Hello and welcome to a presentation in the Treesearch and WWSC Science Center virtual conference series. This conference series was initiated to contribute to the scientific discussion in a time when conferences have been cancelled due to the COVID-19 outbreak. The full program is found at the Treesearch webpage. My name is Josephine Illegård, and today I have the pleasure to present today's speaker, Professor Lars Berglund from KTH, who will present transparent wood and other materials from the delignified wood. Lars is professor at KTH and was the director of WWSC Science Center from the start in 2009 until April 2020. You in the audience can interact and ask questions or comment via YouTube chat function. For that, you need to be logged in and have a YouTube channel. And the questions will be answered after the presentation, which will last approximately 30 minutes. And with that, I hand over to Lars.
Thank you very much. I'm just going to get my screen up here. It's a pleasure to have this opportunity, and of course it's an experiment. I'm sitting at home talking to my computer, but I will try to do my best. So the topic is transparent wood, but I will try to bring out other topics as well. So this image, I think, is a good illustration for what I have in mind. During the last 10 years, I think it's fair to say that the forest products research area has very much been dominated by nanocellulose research. So in other words, the right-hand side image here. And I think it's apparent also that we will see many new products based on nanocellulose, but it will take time. And I think the coming 10 years will show a lot of product development in this area. But from a research point of view, it's actually also very interesting to consider the possibilities to use some of the knowledge we've acquired and start to think about what we can do with nanostructures in wood tissue and in wood fibers. So my two objectives are, can we control the nanostructure in wood-based cellulose materials? And if we can control the nanostructure, what is the significance? I don't think that's completely clear. So let's start from
Sorry to interrupt, Lars. Can you try to share your screen again?
Ah. There you go. Does it work now? Okay, good. So I'll just go straight to the slide I intended to present. So on the right-hand side, you see the cellulose nanofibril, which represents sort of mainstream cellulose research today. But what I have in mind is to discuss the possibilities to bring the knowledge we've gained by studying nanocellulose to fiber research and wood research. Can we control the nanostructures? And if we can do that, what is the significance of that? So I wanted to start then with cellulose nanofibril activities in our group. This is obviously still very interesting because we are basically creating small building blocks that can be used to shape completely new material structures. One of the interesting new things is to try to make fibrils which still contain lignin. So this is work in collaboration with RISE, Fredrik Berthold, Tom Lindström, and Erfan Olay is the student working on this. So as you can see, he starts with unbleached kraft. And the hypothesis was that it would be possible to find an optimum in lignin content and in charge, so that it would still be possible to mechanically disintegrate fibrils, although there is lignin in the fibers where we start. And the center composition here with the 11% lignin, so kappa 65, is actually very suitable to make fibrils from. And perhaps interesting is also, if you look on the right-hand side here for the stress-strain curves, the properties of these films are actually not that far away from the best fibril films that we can make from, for instance, tempo fibrils. So if you look at the supernatant structures here, so basically you carry out your kraft pulping, and then you use traditional microfluidizer homogenization. If you take the supernatant and then you look at the fibrils in TM, you can see here we have a 500 nanometer scale bar here. So you can see some of the fibrils are actually of very fine diameter, although some of them are larger. So we can see that perhaps the largest are 70 nanometers or something like that. But if you look at the distribution here, you see there's a large fraction of the fibrils that are actually fairly small. So that's an interesting possibility. Another more interesting, perhaps from in the crossroads between biotechnology and material science, is work by Chi Zhou and his students Sally Koskela. So they're using LPMO enzymes. We have used enzymes previously, endoglucanases, for pre-treatment of fibers of chemical pulp to facilitate fibrillation. But here the idea is different. The LPMO enzymes are actually able to oxidize cellulose. So they create carboxyls by cutting the cellulose chain and oxidizing the end. If you look in the upper left corner here, you see the control. And these are the two fibril materials made using the LPMO enzyme. And if we look at carboxylate content, you see it's substantially higher than the reference. The reference gets the carboxyls from the hemicelluloses, but they're able to increase the carboxyl content, and this is why they see such fine fibrils. So the high resolution TM image on the right-hand side, you see that the fibrils are actually very, very fine. And the properties of films from these LPMO treated pulp fibers are actually quite good. So it's the same idea as with enzymatically pre-treated pulp, where you make fibrils, and you actually get slightly better properties. The strength is something like 250 megapascal and with high modulus. So this is a new approach towards making fibrils. This is where we spend a lot of our time at the moment, on holocellulose CNF. So by mild delignification, we managed to preserve a large extent of the hemicellulose. So we have 28% hemicellulose, very high molar mass because we're not degrading the cellulose, and substantial electronegative charge. So by disintegrating in a very simple way, just using a kitchen blender, we can create these very interesting CNF fibrils. However, one disadvantage, I would say, by starting with fibrils, so the advantage, of course, is that you have a lot of design freedom. You can create a large variety of materials. But if you're going to control the nanostructure, it actually becomes quite challenging. This is a work carried out by Dr. Sueta, who visited our lab from University of Tokyo. So what he did was that he started with tempo fibrils. So if you see in the left-hand side here, we have electronegative carboxyl groups. And then he added polyethylene glycol, which has electropositive charge at the end. And then he can control the density of his grafts. And by controlling the density, he can then control ductility of his nanocomposites. He has something like 2.5% cellulose and then he can control the ductility. So this is very well-controlled material, although from the point of view, if you compare with native structures, this is TM image in the lower right corner here, you see there are still PEG-rich blobs here. So it's not that easy, and it's very, very tedious to control the structure. So for this reason, it's really interesting to try to use the native structure and its existing nanostructure. And what we have proposed in many of our recent studies is that the fibers themselves, if you do very mild delignification, you maintain cellulose molar mass, you maintain the distribution of hemicelluloses. And if you look at this SEM image, you see that the fibers are really straight. So when we make materials from these fibers, they show extraordinary properties. And we're quite convinced that this is related to the fact that we're preserving the structure of the cell wall so that the cellulose becomes much more efficient in its function. If we compare different materials from hollow cellulose, here we have 3 different types. So lower left micrograph, this is paper, so to speak, based on these hollow fibers, 49% porosity. The next one is compressed. We only have 20% porosity. So these are the types of materials that Apple are using in their novel packaging materials, very dense materials. And this, on the right-hand side, we see conventional nanopaper films. So if we look at the properties for hollow fibrils, we get 300 megapascal strength. But the interesting thing is that these compression molded fibers, they show 200 megapascal in strength. That's not bad at all. And I think in many practical cases, those properties can really be used in real structures so that we can make use of the cellulose part. And the paper structure also has extraordinary properties. Despite the fact that the porosity is 49%, we have 100 megapascal strength. So there are many plastics that don't reach that kind of level. So we think that the hemicellulose, we have shown with reference experiments that the hemicellulose has a very important role there in improving the stress transfer. So this is another example from a published paper. So if he measures graft density and relates that to moisture content, so moisture content here, if you have very high graft density as you get with the acetic acid procedure, and you compare it with the bulk procedure, the moisture content is much lower. So another effect that we obtained from this is that we lower the moisture absorption of our material by this fairly straightforward procedure. And actually, it really helps properties of thermoplastic composites as well. I can, because basically what happens if you do melt processing of these fibers, they will disintegrate and form nanofibers in the process. So can we extend this concept? Well, one way would be to think about these types of delignification procedures on wood. And if you carry out this, if you look at the lower micrograph, this is a cell wall here. And if you look at it in very high magnification, you see cellulose fibrils in the lower left corner, and then you have the matrix of hemicelluloses and lignin. If you delignify, you change the color completely, it becomes white. We remove the lignin in the cell wall corners, and we also remove it inside the cell wall. So we create nanoporosity, which is of great interest for modification of materials, and we can get quite high specific surface area. And perhaps the most well-known example where we utilize this is in transparent wood. So This is something which is quite interesting from the, let's say, phenomenological point of view, but the procedure is quite straightforward. You basically remove chromophores from lignin. You can either remove all of the lignin, well, most of the lignin, or you can just bleach it. Then you fill with polymer which has the right refractive index, and then you don't have the same amount of scattering sources, and you can have fairly good optical transmittance. So we've used this for many different applications. For instance, you can add quantum dots and create load-bearing luminescent materials. What we're aiming for there is white LED light, that light sources that can carry load. You can also use it for waveguiding. The group of Sergei Popov and colleagues in Chista have worked together with people in our group to create this laser. It sounds like science fiction, but it's actually quite interesting and has many applications. Another application is heat storage. Celine Montanari has used phase change materials. And perhaps the most interesting there in a nanostructural point of view is that the polyethylene glycol that has the function of phase change material that stores heat is impregnated into the cell wall. So we're really using the nanostructure. The nature of light transmission in wood is actually quite interesting. It's highly anisotropic. And this is a study by Elena Vasilieva. And what she has done is that she measures the intensity distribution of scattered light. You can see here that it's anisotropic. And she measures the scattering angle distribution. And the interesting thing is that if you provide polarized light, you completely change the intensity distribution of your transmitted light. And what she discovered was that this is very different for different types of materials. So if you look at the upper right corner here, you see ash, birch, balsa. So they have qualitatively related behaviors, but there's a large difference between the different wood species. And it turns out that the reason is that they have very different microfibril angles. And this property turned out to be very sensitive to polarization effects. So in many cases, you would like to reduce the anisotropy. And then obviously you can borrow inspiration from plywood. So you can make multi-layered materials. You can either have cross-ply laminates like this, or you can have quasi-isotropic layers in order to reduce anisotropy for the applications where you are interested in that. And then of course you go from highly anisotropic transmitted light to much more isotropic. And you see this diffused quality of light is actually something that is quite interesting in the context of indoor lighting. Diffused light is attractive. So Qi Liang here, he also included quantum dots so that he had a luminescent effect just as a demonstration. But there are many possibilities to modify these materials. If we think about the basics for this, what are the mechanisms? This image can be quite helpful. And the reason we're interested, of course, is that we would like to make thick structures that can carry a lot of load, but still have substantial optical transmittance. We will have some light reflected at the surface. So if you have a very smooth surface, you can to some extent limit that. Some of the photons will be backscattered. They will see fibers inside the material and go back. A large majority of the photons will go forward, but they will scatter. They don't go straight through, they scatter at a certain angle. And this is what we've tried to understand in our project. So the first task we needed to address is the thickness dependence. If you look in the literature, also for nanocellulose films, it's a complete mess. It's so difficult to compare data from different studies. In many cases, there is no report of the thickness of the material. And of course, you need to know that. The most common way of addressing or estimating the thickness effect is the Beer-Lambert law, but for scattering materials, it's actually not applicable. So for this reason, Hui Chen investigated this, and he basically acquired data as a function of thickness for various types of transparent wood. And basically, the model he's using is physically sound. It takes anisotropy into account. So you see these terms take the anisotropy of scattering into account. Mu here is the absorption coefficient. Some of the light is absorbed, although not that much. And D is the thickness. But he basically lumped all these with the exception of he took one attenuation coefficient that he determined experimentally and used this simple expression for transmittance because he saw that it was exponential. And then he predicted data for another thickness, much larger thickness. So in this case, it's 1 centimeter. And it turns out his prediction from data at much lower thicknesses are very accurate. And we can therefore use this to predict transmittance at other thicknesses. And you also notice that if you don't acetylate your wood substrate, you have much lower transmittance. And in this case, the reason is that you have delamination between your polymer and your wood cell wall. If you acetylate, you reduce the amount of moisture in your material. Even if you dry your wood substrate, there is enough moisture there to influence your adhesion between the polymer and the cell wall. So this is why we get better result for acetylated wood. I wanted to say something also about mechanical properties. This is Erik Ljungstedt's work. Delignified veneer is actually a very interesting component for many applications. If you impregnate them with PMMA and you do it very carefully, you basically fill all the porosity. This is birch, but even the lumen in small birch fibers are completely filled. And the question is, what kind of properties can we then get? And we can really improve strength of compared with neat birch. So this is he gets strength values of 250 megapascal. He gets a modulus of 20 gigapascal, although he only has 25% of wood in his composite. And his properties are significantly better than both for neat birch and if you don't delignify. It's interesting to look at the strain fields that he measured. At low strain, we have some inhomogeneity here where we have higher stress. Sorry, yes, precisely. This is the larger strain, and it's related, of course, also to higher stress. Here is at high strain, and there you see that the fracture initiates in this high strain region, and then we have very dramatic failure of our material. In the transverse direction, we actually see substantial improvement. So for the composite, we have a strength of 20 megapascal, and for neat birch, it's only 4 megapascal. It's simply a porous material where we initiate failure at very low strains. The interesting thing is when we analyze the properties of the wood tissue itself, so if you look at the image here, if we just analyze the properties of the solid wood tissue, and we use conservative micromechanics models, neat birch gives modulus of 40 gigapascal. If we then impregnate with PMMA, the effective modulus of the cell wall is 47. So in other words, we transfer stress in a much better way. And if we delignify, we do even better. We reach an effective modulus of 70 gigapascal, partially because we have higher cellulose content, but we also have much better stress transfer. And if we calculate the intrinsic cell wall strength, it is as high as 960 megapascal. So that's, it seems our wood materials are much better than we've thought in the past. And of course, the reason is that we have so much inhomogeneity when we use it as a porous material. I wanted to finish off with some examples of other routes to functionalization of wood. This is work by Jonas Garemark and Junjun Lin primarily. So what they do is that they take the delignified wood scaffold, and then they partially dissolve the cellulose and precipitate it. So they manage to create aerogel structure inside the lumen, and they measure a specific surface area of 220 square meter per gram. And that, of course, is very interesting for functionalization purposes. We know from earlier work that we can diffuse nanoparticles from colloidal suspension into the wood tissue. This is clay. So this is the lumen, this is the cell wall, and these are EDX data showing that we have silicon inside the cell wall. So, and the reason, of course, is that the size of the porosity in delignified wood is perhaps 90 nanometers, and some of the low particles of clay nanoplatelets are small enough to diffuse into that space. And the final example is water splitting. This is Junjun's collaboration project with the Li Cheng Son. So I think we're getting somewhere here compared with charcoal used in our barbecue. Basically what they're doing is that they carbonize wood in a very controlled manner, and they want to utilize the microfluidic character of the lumen channels. Then they functionalize this with catalytic particles, and they grow entities here from lumen that can provide catalysis. So basically, you want to split water. And if this is successful on a large scale, that could contribute to the hydrogen economy. So it's electrocatalytic water oxidation. And this is basically what the structure looks like. So they managed to create these thin carbon nanotubes, which have catalytic particles on the surface. And they really measure high activity in these materials. So it actually works. So I'll finish off with an overview. Previously, we have done additive modification of wood, coatings, lumen fillings. We've been doing grafting, cell wall filling, for instance, with polyethylene glycol, as has been used for the Vasa ship. Now we're also doing subtractive means combined with functionalization. So we remove lignin. We can dissolve and precipitate and create new cellulosic structures. If we carry out bleaching, for instance, we are removing certain functional groups, but I'm sure we can bring this further. And we can also do it inside the cell wall. And carbonization is, of course, very interesting in the context of device preparations. So if I finish off with some conclusions, by using mild delignification, it's really possible to preserve the native nanostructure and the hemicellulose distribution. And I think we've been able to show that this translates into extremely good properties of wood itself. If you do this for only wood, for the fibers, so for the hollow fibers, we have much improved mechanical properties. And it seems also that the hemicellulose distribution is very favorable for binding between different fibers. And of course, the advantage is that it's much easier to process fibers than fibrils at large scale and of high amounts. Delignify wood, we can use the orientation. We don't need to do bottom-up orientation of the fibrils because they're already oriented. We can use the fluidic channels that the tree is using. And we can carry out various types of functionalization of the cell walls to create novel materials. And finally, I think it's really interesting that the biocomposites performance is so impressive. The data we get are way above what is in previous literature. And I think, well, one reason, of course, is that we improve the stress transfer between the polymer matrix and the cellulose at the nanoscale. We improve the stress transfer at the fibril level. And this I think, is very promising for the future. I'd like to acknowledge funding from the Wallenberg Foundation, from ERC, and of course, all my co-authors, in particular PhD students. I think one advantage from the point of view of an advisor is that PhD student projects, they go on for 4 years. You really have time to go in depth into a topic, and that's something I really appreciate. Thank you very much.
And thank you very much, Lars. There were a lot of interesting and impressive examples. You in the audience, now you have the chance to ask Professor Berglund some questions. So far, we haven't gotten any. But when you talk, I can ask a question then. When you talk about modifying wood and wood veneer, how thick pieces are you using, and how thick do you think you can modify?
So it is actually possible to take a plank and delignify it, but then of course you do run into problems. I mean, you have the same challenges as a pulping factory has. If you're going to delignify a wood chip, you have some heterogeneity. You delignify faster in the outer part than you do in the inner part. But of course, you can compensate by doing it really slowly. So that's what we've done when we've done thick parts. But I think from the point of view of industrial scale, perhaps a better approach is to really work on veneer, because there you can do delignification quickly, and you can laminate your materials the same way as industry is now creating plywood or laminated veneer lumber.
So take the opportunity to ask questions via YouTube's live chat function. I take the opportunity just to do some advertisement for next week's seminar, where we have Thomas Rosén, who from KTH, who will present alignment and nanoscale dynamics of flowing nanocellulose, and it will be on Tuesday at 10:15. Anastasia is writing using the YouTube live chat. She's saying just thank you very much for a great presentation. I agree.
Well, it's a bit peculiar, but we do what we can. I think maybe it is interesting to notice how we have worked on nanocellulose for more than 10 years, and now we're beginning to realize that we can bring this knowledge into the creation of, for instance, very interesting wood materials and even devices based on wood structures. And I think there will be many interesting concepts coming out of that research.
Yeah, and that has been a big part of the Wallenberg Wood Science Center, I guess, with working cross-disciplinary.
Yes, yes.
And the examples you've shown are really good examples of working cross-disciplinary. So do you want to add a final comment before we close this presentation?
No, I'm fine, thank you. Thank you very much for the opportunity.
And thank you very much. And thank you all who were listening and watching. And don't forget to check out the next presentation and the coming presentations. Thank you.
Thank you very much.